March. Kindly take a note of it. And also we are having a lecture on Sunday also. तो आप ये ध्यान रखिए कि संडे के दिन भी हमारा लेक्चर रहेगा। और हमारे पास में आप देखिए कि 31st को छुट्टी रहने की वजह से 30th के दिन हमारा दोनों भी लेक्चर रहेंगे उस दिन। और आप देखिए कि एनओसी जो है, providing no objection certificate from the head of the institution. If you are working in the university, it is the registrar. If you are working in a college, it is a college principal. Providing NOC is a mandatory part. No certificates will be issued to the participants, those who have failed to produce an NOC. Kindly take a note of it. पार्टिसिपेंट जो एनओसी सबमिट नहीं करेंगे उन्हें सर्टिफिकेट नहीं मिलेगा, irrespective of their attendance in this course. So kindly take a note of it that NOC is a mandatory part. No holidays are there because we have to wind up this course before 31st March, and 31st March being a holiday. So continuously all days lectures will be there starting from 23rd to 30th March. सिर्फ 30th मार्च के दिन अर्ली मॉर्निंग भी लेक्चर रहेगा, आफ्टरनून में भी लेक्चर रहेगा। एंड ऑल द डेज द लेक्चर विल बी फ्रॉम 2:30 to 5:30. काइंडली टेक अ नोट ऑफ इट। इन योर व्हाट्सएप ग्रुप you will be provided with a detailed timetable. Kindly take a note of it. So if you are having any query, you can unmute and tell me. I have given just the permission before the guest join to unmute. So we are just waiting for the resource person to join our cloud meeting. The guest of today's session, Director of Board of Exam and Evaluation of our university, Professor B. N. Dole, sir. We are just waiting for him to join.
Good afternoon, sir.
Yes, Pandey ma'am, you can tell.
Sir, as I am a research scholar here in Sikkim University,
Yeah.
so a registrar will not provide me
No,
any NOC.
if you are a research scholar, you can take an NOC from your research guide.
Okay, okay. Thank you, sir.
Hello, sir.
Yes.
I sent my NOC on that mail. Kindly check it.
Okay.
It's okay or not.
Hello, sir. Hello, sir. Am I audible, sir?
Yes, sir.
Sir, since we are in a university system, it is not easy to get signature from Vice Chancellor in NOC, sir. Will
No,
it be
it is
possible
a
to get it
registrar.
signed,
In which university you are there, Mishra sir?
sir, SRM University? So will it be possible to get it signed by the head of the department,
No, no, no. Registrar will require. Because
registrar, right?
as a university system, the head of the department, he is not authorized to provide you a relieving letter or a no objection certificate. It is a registrar who will provide you. We will accept it,
Okay.
but it will be a technical problem for you in future. So better is to get it from registrar.
Sure, sir. Sure. Okay. Thank you, sir.
Sir,
Yes, sir.
sir, this is Homnath Vital from Sikkim. Sir, can we get one more day to submit the
Yeah,
NOC?
yeah. No issue, no issue. You take one day, no issue.
हेलो हेलो
हाँ बोलिए मैडम.
Hello, am I
नमस्कार
audible,
नमस्कार
sir?
सर
वन बाय वन,
नमस्कार
वन बाय.
सर
यस, मंगला मैडम. हाँ
हाँ
मैडम.
बारामती से बात कर रहे हो सर
जी बोलिए मैडम.
प्रधानाचार्य जी आज नहीं थे
जी
तो मैं कल तक भेज दूं
जी,
एनओसी
भेज दीजिए, भेज दीजिए.
जी जी मैम जी सर जी थैंक यू
Hello, good afternoon, sir.
जी गुड आफ्टरनून सर.
Sir, may I know that do we have any sir outline of the course, sir,
A
in
timetable will be
PDF form?
provided to you, and you see that this is an last orientation and sensitization course. And what we
Mhm.
have tried in this course that to get an overview of the national education policy, new education policy, and the
Mhm.
major component like IKS, skill-based development, ICT. So you will get a timetable. And you can go through the timetable, sir.
Okay, sir.
सर बैनर स्टार्ट करना है.
हाँ सर का कैमरा वो ऑन करो गौरव पहले. So we have been joined by our guest, Director of Board of Exam and Evaluation of our university, former Head Department of Physics of our university, a person with a vast teaching, research, academic and administrative experience. Professor B.N. Dole has joined today as a chief guest as well as the resource person. So before going to the formal introduction, I would now request Gaurav to start the university song and the banner.
इतिहासाचे जनमनाचे गीत आमुचे जागराचे गीत आमुचे आकाशाचे गीत आमुचे सागराचे इतिहासाचे जनमनाचे गीत आमुचे जागराचे
अभंगाचे ओवीचेही माय बोलीचे माहेर
वाऱ्यातही मराठीचे दिवे लख घरोघर संत महंतांचे विरागी गीत आमुचे कागडाचे इतिहासाचे जनमनाचे गीत आमुचे जागराचे तंतु तंतु संघर्षाचा पैठणीत भिनलेला
नक्षीतच पक्षी पक्षी विजयाचा मिळलेला
सोन पहाट उदयाचे गीत आमुचे उजेडाचे इतिहासाचे जनमनाचे गीत आमुचे जागराचे प्रज्ञेचा सूर्य नवा शब्द शब्द उजळून गेला समतेचा संगराचा अर्थ ढाळून गेला विराट विशाल संस्कृतीचे गीत आमुचे जीवनाचे इतिहासाचे जनमनाचे गीत आमुचे जागराचे गीत आमुचे आकाशाचे गीत आमुचे सागराचे इतिहासाचे जनमनाचे गीत आमुचे जागराचे
Thank you, Goro. You can stop the university song and the banner. So, the chief guest of today's function, as well as the resource person, Professor B.N. Dole, sir, has a vast teaching and research experience. He is also associated with Indian Physics Association as a life member, then Physics Society of India, then Indian Association of Physics Teachers, then Marathwada Janta Vikas Parishad. He is a life member. Then Material Research Society of India, he's a life member. He has also been awarded as an ideal teacher way back in the year 2015 by Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhajinagar. Also, he has been collaborating with CMET, Chirlapalli, Hyderabad, then Tata Institute of Fundamental Research, Kolaba, Mumbai. Also, Intra University. He has been associated with the Intra University Accelerator Center, New Delhi. Also, he has vast teaching experience right from research assistant to professor and head department of physics. He has headed Department of Physics way back in the year February 2022. Also have worked as in charge for Consolidated Material Physics Laboratory, then Library of Department of Physics. Then also he has worked as a warden, program officer. Then he has been also served as a chairperson, Board of Study in Physics of Dr. Babasaheb Ambedkar Marathwada University. Also, he has been the in charge head of Department of Electronics of our university and Department of RUSA of our university. Under his able guidance, many students have completed their PhD, and he has also around six research projects completed. And also, he has international linkages with Dr. A. Branvo, Moscow University, Moscow, and Memorandum of Understanding with Dr. Elise, Department of Electrical Engineering Technology Education Institute of Western Greece since the year 2018. Also, he has been a member of various committee of our university. Also, he's been worked as a reviewer of many journals, reputed journals. Also, he has chaired several session in the conferences and workshop. He has also penned many articles in the newspapers. So indeed, it is really a pleasure and honor for all of us to have him here as a resource person, as a chief guest. So again, I welcome him, and I would now hand over the session to Honorable Professor B. N. Dole, sir. Over to you, sir.
Thank you, Professor.
Yes, sir.
Where is
Yes, sir. Within a minute, Gaurav will come to assist you.
Gaurav.
Yes, yes, yes.
Gaurav, have you loaded this? Presentation is loaded. Yes. Oh. इकडे घ्यायचं करू द्यायचं असंच.
नाही ते ओपन होतं सर आपण ते पीपीटी सांगितलं चेक करून ते शेअर करायला लागेल ठीक आहे ठीक एक मिनिट
Okay. Thank you, Professor Rafe, sir, who is the Deputy Director of this EMMTTC and Director and my colleague, Professor Dhanasri Mahajan, Madam. Today, this is a very important event because I got this opportunity to share my research articles, research work with the participants, those who have joined from the corners of India and Maharashtra as well. And what is the important of the research? If we find that one, that is very innovative, things will come out. If we share, if we discuss. Today, I would like to share my ideas regarding this one and to just discuss the concept which I have worked in my laboratory. So the topic of today's talk is advanced materials for futuristic applications, its innovations, and what are the possible opportunities. So in this way, I would like to just discuss and then they interpret the things. If we use the material and then the advanced material, means we people are well known with this material, and there are the number of materials, large, huge number of materials, colossal materials are there. But we have to think about its shape, size, and volume also. Means all these things are already confined in this. But what are they? Means these materials are there. For example, the stone is there, but what is the use of the stone? Irregular shape of the material, and if it is a irregular, then we have to bring it into a regular shape, and then we think about that one. If this is a irregular shape and size of the material, of the stone, this stone has irregular shape and size, is it useful or not? And if you want to use it, then we have to just bring the same into definite shape and size, and then we can say. But you see, at this bulk level, we think about this one. Then if we go to the mic, that is a milli and micro, and then nano, then that is again useful. So it means at the bulk level, material has limited applications. It means we can say there are the limitations. But if we go to downscale, who is talking? Please, hello, somebody is talking. Mute your mobile. So I was talking about this, the material. Means you see, if you go to the downscale, means if you scale down the material, then what are the possible properties? What are the applications? So see, if from the stone, we crush the stone, and then from that stone, we get this cement, very fine particles. Means the bulk to the means the scale down, and then see the application of that material for the building blocks. No doubt, there is that remedy, there is that process, but we followed the process, and then initially that material was not that much applied, limited applications it carries, but after that, see the application of that one. So in this way, we have to think over the material, and then we can say the material from bulk to micro, and from micro to nano, then there are the plenty applications material have. And if the materials have the plenty applications, then we can say these are, even though this is the classical example, but if we think about the manganese, chromium, cobalt, all these are the materials and elements transition. If you in periodic table, these are the transition metals, and if these materials, if we select from these, then what are possible applications of these materials? One can think over this. Now suppose the chromium, cobalt, chromium and cobalt, manganese, these are the materials, and if we use, so again the another useful element, useful material is there, that is the zinc and oxide. Zinc oxide, this is the again the material, and ZNS, zinc sulfide, this is also the material. And if we use these, which the elements, the transition metals, TM, that is the chromium, cobalt, iron, nickel. If we use these elements and if we dope these elements into the ZNO lattice and ZNS lattice, what would be the effect? And for this, we have to follow, okay, step by step. If I talk regarding this one, then without the slideshow, without the presentation, the talk will continue and you people will get bored here. So I will touch to the slide. Now you see, this is the first slide of my presentation. Ooh. Just a minute. Pardon? Now here there is that rapid development, enhancement, and there is also the demand for high performance materials. The materials have the high performance, then there is also the demand. Advanced materials including the functional materials, functional composites, smart materials, meta materials, and nanomaterials. They have the tremendous industrial applications. For example, the energy storage and biomedical applications. These materials show the unique mechanical, optical, and chemical properties, making them essential for next generation technology. Now my presentation outlines that the innovations in advanced materials focusing on emerging trends, fabrication techniques, and novel applications. Now, this presentation will highlight the commercialization and industrial adoption opportunities, addressing scalability, cost effectiveness, and sustainability challenges. The important topics of this, it covers the materials, namely graphene, emulsions, and transition metal for energy storage, photocatalysis, flexible electronics and sensors, nanocomposites and hybrid materials for enhanced mechanical and thermal performance, metamaterials for photonics, nanocomposites, as I mentioned, that were mechanical and thermal performance, electromagnetic wave manipulation and stealth applications, bio-inspired and smart materials for biomedical, self-healing and adaptive technologies, sustainability challenges, and the role of advanced materials in achieving a greener future. Now here, as I means, you see zero dimensional, that is the nanosphere and clusters, and example is the gold particle, that is the gold nanoparticle. Fullerenes, the quantum dots, very small, that is the nano level. Okay, and these materials means nanospheres and clusters. Here the gold nanoparticles, fullerenes, and quantum dots. These are the zero dimensional material, nano materials. One, that is the wires, rods, and nanotubes. These are the carbon nanotubes, gold nanowires, okay, and metal nanorods. So one dimensional. Two dimensional, there are the three thin films, graphene sheets, okay, graphene sheets, and layer nanomaterials, and this is the carbon coated nanoplates, means thin films, graphene sheets, and layered nanocomposites. These are, it means thin films and layered structures, plates. Okay, these are the examples of the 2D and 3D, that is the bulk nanomaterials and polycrystals. Okay, this is the polycrystalline, this is the dendrimer, and this is the liposome. Okay, three-dimensional. Now this is the carbon nanotube, and the carbon nanotube are also the two-dimensional. This is the nanomaterials classified into 4 category based on the dimensionality: 0 dimension, 1 dimension, 2 dimension, and 3 dimension. Okay, 1 dimension nanotubes, sheets, that is, sorry, nanotubes, wires, and rods, thin films, plates, layer structures. Now, what are the advanced materials? Advanced materials, this is just the materials, substances engineered with superior properties. Okay, materials engineered with superior properties to conventional materials, now making them suitable for high performance applications across various fields. These materials exhibit exceptional characteristics such as high mechanical strength, electrical conductivity, thermal stability, optical tunability, and chemical reactivity. So here these materials, what are the exceptional characteristics? Means high mechanical strength, that is very important. Electrical conductivity also, the thermal tunability and chemical reactivity, the thermal stability and optical tunability. These properties, they have the exceptional characteristics outlined here: high mechanical strength, electrical conductivity, optical tunability, thermal stability, and chemical reactivity. For example, the graphene, MGen, high entropy alloys, metal organic frameworks, perovskites, and bio-inspired materials. Their unique properties enable their use in energy storage, environmental remediation, biomedical applications, and next generation electronics. Emerging trends in advanced materials. 2D materials, graphene, MGen, TMDS, high electrical thermal conductivity. These materials, two-dimensional materials, how they have the high electrical thermal conductivity, mechanical strength, and surface area. These are, as I mentioned, two-dimensional, high electrical and thermal conductivity, mechanical strength and surface area, energy storage, two-dimensional materials, flexible electronics and sensors, nanocomposites and hybrid materials combining nanomaterials with polymers, metals, or ceramics for tailored properties. Applications: structural materials, coatings, and biomedical uses. Metamaterials means these materials and their applications outlined here. Engineered to manipulate electromagnetic waves, negative refractive index, application photonics, clocking, and wireless communication. These are the metamaterials and used for the wireless communication. Smart and bio-inspired materials, self-healing, shape memory. This is smart and bio-inspired materials. Biometric materials inspired by nature. And this is the application of these wearable technology, robotics, and medical devices. The materials are classified, and the examples of this one and what are they used in their possible applications of these materials. Oxides: titanium dioxide, zinc oxide, iron oxide, tin oxide, aluminum oxide, copper oxide. These are the molybdenum trioxide. Now sulfides, yes, WS2, MoS2, CDS, ZNS, ACNS2, copper sulfide, PBS, selenites. These are the molybdenum diselenide, tungsten diselenide, zinc selenide, cadmium selenide. These are the selenites. Means AC is after metal. Element: tellurides, means Te3 suffixed here for bismuth, antimony, molybdenum, cadmium, tungsten, okay, telluride. Nitrides N2, N, okay, N is suffixed. Yeah, here after the metal N is there, nitrogen. Boron nitride, gallium nitride, this is the aluminum nitride, all this. Carbides, C, TiC, titanium carbide, silicon carbide, tungsten carbide, zirconium carbide, borides, B2, and phosphides, P. Now, dimensionality means zero dimension, that is the gold nanoparticle, then the quantum dots. Here, quantum dot, CTAC, lead sulfide, cadmium selenide, zinc oxide, they have the quantum dots. Fluorines, C60 and C70. Metal nanoparticles, aluminum, gold, platinum, carbon dots. Zero dimensional. One dimensional means here carbon nanotubes, nanowires, nanorods. Means nanorods, nanowires, NR, NW, and CNT, carbon nanotubes. These are the examples. Here the materials with one dimension significantly larger than the other two, exhibiting high aspect ratios and excellent charge transport properties. Two-dimensional, that is the MGen and graphene. Selenide, this is the sulfide, disulfide, molybdenum disulfide, then the tungsten disulfide, and this is the boron nitride and selenide. Automatically, thin materials means thin films, okay, with strong in plane bonding and weak van der Waals interaction between layers, leading to exceptional mechanical, optical, and electronic properties. Three-dimensional metal organic frameworks, MOFs, covalent organic frameworks, perovskites, BaTiO3, bulk metals, and polycrystalline oxides. Materials with all three dimensions extending in space, providing structural integrity and diverse functionalities for various applications. These are the example. Now, synthesis techniques for the 0, 1, 2, 3 dimensional materials. There are the certain techniques, there are the various techniques used to synthesize above mentioned materials. 0 dimensional, 1 dimensional, 2 dimensional, and 3 dimensional, depending on the desired morphology. What morphology we expect, so depending on that, okay, and then we have to just find out the route. We have to select the route. Below we explore these techniques using zinc oxide, titanium oxide, titanium nitride, and graphene oxide. These are the certain examples. Now, the synthesis techniques are given below. The number one, co-precipitation, CBD, Silar, Sol-gel, chemical vapor deposition, CVD, electrochemical deposition, electrophoretic deposition, Hammer's method, and hydrothermal method. Now, one by one, I will describe here. These are the roots. Now you see here, means using these 9 roots, we have synthesized the material. Co-precipitation route used for 0 and 1D nanoparticles. ZNO nanoparticles, the principle of this route is given here. The chemical precipitation of zinc 2+ ions using a precipitating agent. Here the precipitating agent NaOH, NH4OH. The reaction leads to the formation of zinc hydroxyl group, which decomposes into ZNO. Zinc ions NaOH. So zinc, and then this reaction leads to the formation of zinc hydroxyl. ZNO synthesis using co-precipitation. The precipitation of zinc 2+ solution dissolve the zinc dinitrate in deionized water. Addition of precipitating agent, add NaOH under stirring. Formation of zinc oxide precipitate, white precipitate forms. Aging and washing. Let it settle. Wash with ethanol and water. Drying and calcination. Heat at 400 to 600 degrees Celsius to obtain ZNO nanoparticles. Now this is the actual practical method. Here actual practical process demonstrated through these instruments and beakers, and now you can see here, this is the adding zinc chloride in deionized water. Zinc chloride. Then mixing the solution by stirring for 30 minutes at 40 degrees Celsius. Here is the magnetic stirrer. Then, and another solution, here is the zinc dichloride and sodium hydroxyl. Okay. This sodium hydroxide in deionized water. Zinc dichloride and sodium hydroxyl. Now both this means here also magnetic stirrer, here is also magnetic stirrer. Both the solutions taken into one beaker, and here is the pipette. Now you see all the solution. Now obtain here, taken after thorough. So here using the after thorough stirring, both the solutions taken into one beaker, and then obtain precipitates here. So NaOH solution pour drop wise. Again here this NaOH prepared zinc dichloride homogeneous solution. Here we obtain. So precipitate here.
सर आला एक फोटो काढला मला लिंक पाठवली हा ओके
Okay, now you see this is the actual experimental procedure which I demonstrated. Now you see initially here was the deionized water and the material. Lastly, what we got here, the zinc oxide nanoparticles. Now you see this is the white powder, and this is means in the form of nanoparticles. After this means thorough discussion, means thorough mixing, and this material stirred. Lastly, we got this. Okay. Chemical bar deposition, another method used for one-dimensional and two-dimensional nanoparticles, and we can prepare here the thin films. Means the example of TiO2 thin films. This is the chemical bar deposition method. Now, what is the principle of this one? A controlled chemical reaction in an aqueous solution forms a thin film on a substrate. Okay. So here we use this chemical bar deposition method for the preparation of the thin films. So using this substrate, we can deposit the particles on the very sharp and plain glass substrate. The flow chart of the same is given below, but before that, what is the methodology? So precipitation of solution, dissolve titanium tetrachloride or titanium disulfate in water. Then the addition of complexing agent, that is the NH4OH, to control pH. Substrate immersion, deep glass or FTO substrate. Now, deposition process, titanium oxide nanoparticles nucleate and grow. Annealing and characterization, heat this solution at 450 degrees Celsius to form the phase. Now, this is the actual process. This is the experimental demonstration. Okay. The third method is the successive ionic layer adsorption and reaction. Okay. Cellar method, that is used for 1D nano structure materials. Titanium nitride, we can. Now the flow chart of the method is the titanium nitride synthesis using cellar, cationic deep substrate dipped in titanium tetrachloride solution, rinse with water, remove excess precursor, anionic deep substrate dipped in NH4OH for reaction. Repeat steps. This is the multiple cycles for uniform film growth and the annealing heat, and this one, the 500 degrees Celsius in N2 atmosphere. Now you see, this is the glass substrate technique. This is the cellular technique. Here is the precursor. Okay, this glass substrate is deep into this, and then here the adsorption of particles. Then use the deionized water. This is the titanium plus ions. Okay, titanium ions. This is the water. Here is the adsorption of this. Then after the removal of these ions, okay, loosely bound cations, okay, loosely bound, these are the loosely bound. Here is the completely, these are the strongly bound, and these are the loosely bound. Then these are the removal using the distilled water. Then you see, these are the strongly bound. Then again, anionic precursor, that is the titanium ion, and here is the adsorption of anions. Now these are the anions, and these are some particles from these are also dissolved here, and these are again loosely bound. Remove the loosely bound using the distilled water, and now you see this. These are the thin films. Now Sol-Gel method, this is up to 2-dimensional, 0, 1 and 2 dimensional material. Using this method, we can synthesis, we can prepare the particles, nanoparticles, okay, Sol-Gel method. So dissolution of titanium precursor in isopropanol, hydrolysis and condensation, add water and acid catalyst, gel formation, allow slow polymerization, aging and drying, remove solvent, calcination, heat at 500 degrees Celsius to crystallize titanium dioxide. This is the steps involved for while preparing these using the Sol-Gel method. Then the fifth route is the chemical vapor deposition, used for 1-dimensional, 2-dimensional, and means 1 and 2-dimensional. This chemical vapor deposition. Titanium nitride, here is the principal gas phase reactants. Here the gas formed, the material is heated up to the formation of the fumes, and these fumes are deposited on the thin films for the nano structures on a substrate at high temperature. Now this is the flowchart for titanium nitride synthesis. Using the chemical vapor deposition means we have to form the chemical, use the chemical into vapors, fumes. So these means here titanium tetrachloride and NH3 gases flow into chamber. Reaction at high temperature up to this 600 to 800. Now titanium nitride deposition on substrate reaction produces titanium nitride thin films. Post-treatment and characterization. SAME and XRD for structural analysis. Now electrochemical deposition. This is again very viable method used for one-dimensional and two-dimensional films. So titanium oxide, this is the electrode, uses electrochemical reaction or oxidation on deposit or to deposit titanium oxide from a solution. So this electrochemical deposition, electrolyte solution we have taken here, that is the titanium tetrachloride in ethanol or water mix. Electro deposition on cathode, TiO2 nanoparticles form under voltage. Rinsing this, rinsing and drying. Remove excess electrolyte, and we have to give the heat treatment to this to improve the crystallinity of the material. Now this is the TiO2 and ethanol. Okay. So here the anode and cathode, you see here. This is the voltage is given, and then the deposition of this at this cathode, and this is the anode. Okay. Means here this is the thin film. Here the material is deposited of, this is the substrate, and then the material here, this cathode, means use this cathode as a cathode, this is anode. Electrophoretic deposition, and this method used for 2 and 3D nanostructures, means up to 6 methods. So we synthesize 2D, but thereon. Now you see the 3D, 2D and 3D now. Graphene oxide thin films. Quite difficult, but we synthesize using this. What is the principle? Geocolloidal suspension. This is deposited under an electric field onto an electrode. Means this electric field deposited under the electric field onto an electrode. Now what is the importance of this method is deposition, geo deposition using electrophoretic deposition. So here geo suspension, disperse geo in water or ethanol. Use the conductive substrates, that is FTO or glass. Apply electric field. Geo moves towards the electrode. Remove solvent and anneal at 200 degrees Celsius. Now, these are the means this is the substrate now. Okay, this is the substrate, and here the material, nickel ions decorated geo. Nickel ions decorated geo. Okay. Hammer's method now very important again. Used for 2D graphene oxide synthesis. Graphite is oxidized using potassium permanganate and sulfuric acid exfoliated into graphene oxide. The geosynthesis using Hammer's method. Here, the graphite oxidation using this, add KMnO4 to sulfuric acid. Then formation of GO, stir at 50 degrees Celsius and H2O2 to stop reaction. Washing and centrifugation. Remove unreacted species. Drying and exfoliation. Sonicate to obtain geo nanosheets. This is the experimental setup. Hydrothermal, this is the last route. And this route is very useful because you see previous one and this. The main difference is that even Hammer's method, then the sol gel, Silar, electrophoretic, used for synthesis up to 2-dimensional. But this is the route which we used to synthesis, means here limitations, electrophoretic 2 and 3, but not 0 and 1. But here, this route is being used for the synthesis of 0 to 3-dimensional materials. Okay. And therefore, this is the cobalt oxide quantum dots. Zinc oxide or zinc sulfide nanowires. Geo nanosheets. Bismuth oxide nanosheets. Manganese oxide nanoflex. Zinc sulfide nanospheres and nanotubes. Nanoflex spheres and nanotube cubes. Now principle, high pressure and temperature in an autoclave to crystallize materials. Now for this zinc oxide and titanium oxide synthesis using hydrothermal method. These are the zinc dinitride in aqueous solution, transfer to autoclave, heat at 180 degrees Celsius for 12 hours, crystallization and growth, zinc oxide nanorods, cleansing, cooling, washing, and drying. Now this is the route. Here is the zinc oxide, magnetic stirrer. The solution is into this beaker. All this pH is maintained. Stirring 20 minutes, then transferred into this autoclave. Teflon line autoclave, hydrothermal. Wash with deionized water and ethanol. Now this is before and after. simple. This is again quite complex but simple route. Means all the solutions maintain the pH in one beaker, stir it, and then transfer into the autoclave, heat up to 160 degrees Celsius, wash with deionized water and ethanol, and then dry. Then the calcination. Why hydrothermal method? The hydrothermal method is widely regarded as an advanced and highly effective technique because, as I mentioned, that one, the 9 routes out of 9, this route, only this route, hydrothermal method is used to synthesis from 0 to 3-dimensional nanoparticles, and therefore this is very effective route. Now, the most of the means all the routes I covered here, means 9 routes we have used for the synthesis of the nanoparticles, nanowires, nanotubes, nanoparticles, I mean the quantum dots we successfully synthesized. That is, and in my first slide, in the second slide, if you go to see the previous, you will find that one, the gold nanoparticles, then the fluorines, and this means the gold nanoparticles and quantum dots we successfully synthesized using the co-precipitation route, but using this route also, and then the Sol-Gel route, then the Siller technique, chemical vapor deposition, physical vapor deposition, means all these routes we were used. But why this route is important? Because using this route, we can synthesize the material from 0, means dimensionality matters here, and therefore including Sol-Gel, co-precipitation, chemical and physical, the below are the means, here are the several key advantages over other synthesis methods. Below are the reasons why the hydrothermal method is superior. This is the reason here it gives. Now this method is applicable for the synthesis of different dimensional materials, diverse dimensional materials, and therefore this route is useful, applicable. 0-dimensional nanoparticles hydrothermal synthesis, this technique enables controlled nucleation and growth of nanodots or quantum dots. 1-dimensional means the nanowires and nanorods. Okay, nanorods, nanowires. Here, anisotropic growth in hydrothermal conditions allows the formation of well-aligned nanorods, nanowires, and nanotubes. Okay, nanorods, nanowires we can use here. Okay, now this is very important. Okay. So here 1-dimensional means nanowires, nanotubes, carbon tubes, okay, nanorods. 2-dimensional, these are the nanosheets, means the thin films and these are used for the from the graphene oxides, molybdenum diselenide, and sorry, molybdenum disulfide, and MGens. 3D hierarchical structures. These are the complex architectures like flower, core shell, and porous nano networks can be used due to the self-assembly properties of hydrothermal reactions. Now, this is the precise morphology and size control. So the temperature 100 to 300 degrees Celsius, the pressure, reaction time, and precursor concentration can be precisely controlled, leading to the highly uniform and reproducible nanostructures. So here, the anisotropic growth of nanostructures crucial for advanced material applications, eco-friendly and scalable, uses water or other green solvents. This method is useful. Why? Because it uses water or other green solvents, making it an environmentally friendly process compared to sol gel, and therefore we can use this one. Now it has the high crystallinity and purity. The hydrothermal process promotes defect-free crystal growth. So this is again very important. Slow reaction kinetics leading to highly crystalline structures. In contrast, sol gel and co-precipitation methods often require post-annealing, which may introduce defects or impurities. Now you see here. So this sol gel and co-precipitation, in contrast, sol gel and co-precipitation methods, both methods introduces the defects or impurities. But in this hydrothermal method, this is mentioned here, defect-free crystal growth. Synthesis of complex and multi-component nanoparticles. It allows for doping, heterostructure formation, and composite synthesis in single step. For example, tungsten carbide based MnO2 nickel doped CO3O4 nanocomposites can be synthesized without multiple processing steps. Okay, these energy efficient and low processing temperature here. So it works at relatively low temperature compared to chemical vapor deposition and physical vapor deposition. Reduces energy consumption because double the rate here, and therefore reduces energy consumption while still enabling high quality material formation. Controlled surface chemistry for functional applications. Hydrothermal conditions allow for precise control over surface functionalization, which is important for supercapacitors, enhanced charge storage, photocatalysis, increased active surface sites, memristors, optimized defect engineering, and photosensitivity means these material control surface chemistry. So here these materials means used materials. Using this method, we can size the material, and these materials can be used for the designing, for the to design the supercapacitors, okay, and again the photocatalysis, memristors, okay. Now we can develop the supercapacitors using these materials. Now prepare nanometers for the application of photocatalytic activity using this method, hydrothermal method. If we prepare and synthesize the materials, then these materials can be used for the photocatalytic activity, antibacterial activity, sensor. We can make such a devices. Means these materials can be used for device applications, and these are the means photocatalytic antibacterial activities, sensor, supercapacitor, and photodetector. Now means I discuss about the synthesis techniques, different routes, but what actual work we have done in my laboratory, now I would like to share that work with you people. Okay. So you see, near about 1.5 hour I cover. I don't know because you see the most of the participants from means the science background or arts, science and commerce background, I don't know. But I treat you, you are all from the different faculties, maybe arts, commerce, and those are from the science stream. They don't have the problem that much. But those are from this remaining two. So how much they are able to grasp. But you see, I know this is the topic which is very hard, but once we hear the hard, if we concentrate on hard topic, then we can easily understand the simple things. Because if we study the hard, which is not very means easy to understand, and it is very hard to understand, but we concentrate on it and to understand, if after 2 times 3 times study, repetition, then we can understand the hard also. And then the simple, there is no problem. I know this topic is from the nanoscience, and particularly from the physics, and in general from science. This is very tough, but the tough, if one understand the tough, he will be a top. And therefore, I concentrated on this. Now you see, as when I initiated this talk, so I talk about the iron, cobalt, nickel, and now you see this is the iron doped bismuth oxide. Now these materials we prepared, and this work now we prepared, we characterized, and then this work now you see on the screen published in the journal, that is Results in Chemistry. It has the impact factor 2.3. Now these are the crystallographic pattern. This is the X-ray pattern, X-ray diffractograms. These are the plots. Now you see the crystal structure of the samples. Who is talking? Please.
ஆமா இதெல்லாம் உங்க அப்பா தான் முடிவு பண்ணுவாங்க.
NEP Arienti. Mute your mobile. Now you see, these are the XRD pattern, and from this we can calculate the lattice parameters. Okay, lattice parameters. Then they means these are the lattice parameters, and we have calculated the volume cell, crystallized size, dislocation density, lines per square meter, microstrain, and stacking faults. Okay, now you see, and from this one can understand that the crystallized size goes on reducing and volume enhances if the concentration increases. The volume here you see up to 0.5 enhanced and then suppressed. Similarly, again you see the crystallite size decreased, whereas the dislocation density enhanced. Microstrain, again you see 131412 again decreased, initially increased and then decreased. Stocking faults up to 0.5 increased and then suppressed. So you see from the field emission means EFE same. You see these are the here nanorods. You see means if the nanorods, nanowires, can anybody tell me the dimensionality of this as prepared material from the audience? Yeah, participants. Here it is clearly mentioned this structure morphology of the as prepared material, morphology of as prepared material exhibits nanorods. Means what is the dimensionality of the material? Dear participants, can anybody tell me the dimensionality of this material as prepared material? It exhibits the nanorods. Hello, I'm audible. Hello, dear participants.
Yes, sir, you are audible.
I'm audible. I have asked the question here. The
Yes, sir.
material, you see, it is a nanorod. Okay, nanorods. You see, these are the nanorods. On the screen, cursor of this mouse is on this. Okay, mouse. You see, these are the nanorods. है ना? आपको दिखाई देता है क्या? ये nanorods है ना? ये हमने हाँ ये मटेरियल तैयार किया और ये मटेरियल क्या दिखाई दे रहा किससे? क्या हमने ये सेम निकाला, इसका ये फी सेम और ये फी सेम. ये देखो ये जो रेड लाइन है उसके यहाँ मेरा कर्सर है. ये देखो यहाँ क्या दिखाई दे रहा? ये नैनो रॉड है ना? राइट. ये देखो. तो ये मटेरियल की डायमेंशनलिटी कौन बताएगा? क्या डायमेंशन इसका? ये 1 डायमेंशनल है या 0 डायमेंशनल है या 3 डायमेंशनल है? नहीं समझ में आया?
3 डायमेंशनल है वो.
नहीं ना,
3D मैप है सर।
नहीं नहीं नहीं,
वो-
ये नैनो रॉड है ना, ये
नहीं।
देखो नैनो रॉड्स लाइक मॉर्फोलॉजी। तो
हाँ
नैनो
सही है।
रॉड जो है वो 1 डायमेंशन में आते ना, हमने पहले ही मेरी जो थर्ड स्लाइड थी उस पे दिखाई दिया ना, वो 0 डायमेंशन कौन सा होता है, 1 डायमेंशन क्या होता
अच्छा
है। तो नैनो रॉड्स, नैनो वायर्स, ये बताया था ना, नैनो ट्यूब्स। हाँ, तो ये नैनो रॉड है, ये नैनो रॉड दिखाई दिया ना। Then the photocatalytic activity. So this activity we use here to find out the energy band gap. आपको देखो, यहाँ हम क्या कर रहे हैं कि ये जो फोटोकैटालिटिक एक्टिविटी जो है, फोटोकैटालिटिक एक्टिविटी मटेरियल की, तो इससे कितना फोटो डिग्रेडेशन हो रहा, ये निकालना है। फोटोकैटालिटिक एक्टिविटी ऑफ द मटेरियल, जैसा ये देखो 0 to 180 मिनट्स, हाँ, ये ड्यूरेशन दिया। तो क्या अफेक्ट हो जाता है, अब्सॉर्बेंस। ओके, तो फोटो डिग्रेडेशन ऑफ मिथिलीन ब्लू डाई बाय प्योर, एंड this is the concentration 0.3%, 0.5% iron dope, okay, and then iron dope this 0.7%. So these are the things here, and now you see 0 to 180. Now this portion, now you see again here 150, time decreased now, 180 to 150 here. Here is 180 again here, 180. How many cycles it cover? Again, these are the plots, means the plot of time horses C by C 0, and plot of time horses log C by, means capacitance, and what is the variation of the relative concentration of methylene blue dye solution under visible light irradiation in the presence of pure. Now these are the cycles. Why we use the cycles? Photocatalytic efficiency. How the photocatalytic efficiency increased? Why we have to use the photocatalytic? Why we have to study the photocatalytic activity of the material? Because to find out the efficiency, photocatalytic efficiency, and in our material we got the maximum for 5% iron doped bismuth oxide, that is the 93.37%, means 93.37. This is the photocatalytic efficiency. Which one is the highest in this? Now you see the antimicrobial activity here. Which one is the clear? Here you see the 0.5%. This is the 0.5%, means antimicrobial activity of pure Bi2O3, and 0.3%, 0.5 and 0.7 percent iron doped bismuth oxide for different concentrations against bacillus bacteria and aspergillus flaws fungi. Okay, and now you see here, this is the diameter of zone inhibition. So this is the inhibition in millimeter. Here you see, this is the zone of 0.5, and that therefore here is the diameter increased of this one, and that is the highest. Again here 0.5% iron dope. We have used here different bacteria, that is the bacillus. For bacillus, maximum area covered. Here is also maximum for aspergillus flavus fungi. Maximum area is covered here for 0.5%. Here 5%. See, this area is covered, and in other cases it is lower. Here the maximum area, and therefore this percentage. Now, here the geo-based iron doped bismuth oxide, and this work has been published in Ceramic International, which has the impact factor 5.1. Now you see, this is the method geo-based iron doped bismuth oxide nanoparticles we have synthesized, and here again we got the sheets. The crystallographic access, here see, for this we also calculated using the X-ray crystal, means these are the X-ray diffractograms, and from this the crystallographic study we have performed here. We calculated successfully the crystallite size, dislocation density, and microstrain, stacking force, and crystallite size, all these here, and these are the crystallographic parameters. We got the cubic structure, and now you see here the same micrographs for this. Now, if we same micrographs are outlined here, and then ADAX also, ADAX spectra of the same. So, if we say micrographs of geo-based bismuth oxide, geo-based, and the concentration of iron, then the geo-based concentration of iron, geo, and this is the geo-based 0.7% iron doped bismuth oxide, and we got the agglomeration here. This micrographs, okay, these are the micrographs, and this is the energy dispersion. Okay. Element means the composition is calculated here. How much the composition of each element. Okay. X-ray spectra. This is the energy dispersion analysis of X-ray spectra. Oh. Now this is the again the time evaluation spectra of Congo red azo dye degradation by pure and these. Okay. Now you see here the absorbance. This is the absorbance. Now, and this is the plot of time Horse's capacitance here, and it is outlined. It is in percentage given here. That is the blank, and then the samples deposition, and what is its percentage, and then the efficiency here is calculated, and here is the degradation efficiency for methylene orange and methylene blue. Okay, photocatalytic activity, and now that was the bismuth oxide geo-based materials. Here the geo-based tin iron co-doped bismuth oxide nanocomposites. and this work has been published in the Journal of Energy Storage. Its impact factor is 9.4. Now you see. We have published, we have synthesized these materials using, and now you see these are the X-ray diffractograms. Okay, these are the graphs. Yeah, you can say the spectra. And here the crystal structure of the sample is a tetragonal. We found the tetragonal. Now sample shows nanoflake like morphology, nanoflex. Okay. Here the nanoflex. And these are the cyclic altimetry curves of pure bismuth oxide. Then the 5% tin iron co-doped bismuth oxide. Then the GO and pure Bi2O3. Then GO 5% tin iron co-doped. These are the plots of the cycloaltimetry. Then this is the GCD, galvano charge discharge curves of all synthesized samples at 0.1 ampere per gram, and the calculated capacitance of all samples with different scan rates. This is the galvano charge discharge curves of the same. Here you see how much time for charging it takes, minimum time for charging it takes, and maximum for discharging. Here you see this sample means GO based 5% tin iron doped bismuth oxide. This and for discharging, suppose here now you see pure, and this one near about 430. Okay, this time means this table. Now you see 5% charge transfer resistance. Here solution resistance, specific capacitance 1302.5. Solution resistance is 1 point. Specific capacitance, and this is the 0.38. Charge transfer resistance means decreased. There is means resistance decreased and solution resistance increased. Now the Nyquist plot, cyclic stability and Coulombic efficiency of synthesized samples. Now for this sample you see the capacitance and cycle number. Coulombic efficiency, this is the capacitance retention. Now for this, the Coulombic efficiency for this sample geo-based 5% tin iron bismuth oxide. Here near about static, this Coulombic efficiency and capacitance retention decreased, whereas the cycle number increased. Okay, so this is now titanium doped cobalt oxide nanoparticles. Materials today communication. This material means we synthesized and published in this journal. Now these are the X-ray diffractograms. This is the X-ray diffraction spectra of as prepared material. That is the titanium doped cobalt oxide. These are the lattice parameters obtained from the X-ray diffraction spectra, and the sample as prepared material is a cubic. This is a cubic. Now you see for this is the highest value. Oh, very interesting. Field emission scanning electron microscopy, nanorod like morphology. See, it is clearly, okay, you see nanorod like, and the thickness of the titanium cobalt oxide 1430 length. It is in nanometer. Of this is 2166. This is the nanorod length, and width is 31. 68, 58, and maximum is 71. Photocatalytic activity. Time study of the methylene blue degeneration spectra. TCO, TCO1, TCO3, and TCO5, TCO7. The plot of time horses C by C3 and plot of time horses log. Earth cycles graph of samples. Okay, means here this photocatalytic activity found here, the time cycle for this 0 minute to 20, for this is maximum, for this is maximum. Okay, and here is minimum. Now here these are the plots. Capacitance, the degradation efficiency and pseudo first order rate constant of synthesized sample. Degradation efficiency, this one, for this, and pseudo first order rate constant is this point 0.874. Degradation ratio of this, you see, H2O2 for different scavengers, yeah, reactive species scavengers on the degradation sample under sunlight irradiation. Geo-based titanium doped cobalt oxide nanoparticles. Previous one, titanium doped cobalt oxide. Now geo-based titanium doped cobalt oxide nanoparticles. Okay. Now decontaminated water with methylene blue plus methyl orange, Mb plus Mo. This is the, see here, geo sheet. This is the sunlight, H2O, oxidation, OH and OH plus. O2, okay, reduction, water after degradation of dyes. Degradation rate, H2O plus CO2 for 0 minute. Now you see for 0 to 180 minute. This is then suppressed. Here is for this, it is clear. Now here are the structural parameters, the crystal structure of all samples were cubic. Lattice parameters of as prepared samples here, and we calculate the lattice parameters ABC, volume, and here we outline here in this is increased crystallite size, decreased dislocation density lines per square meter, microstrain, stacking fault, and surface area. Sheets, field emission scanning electron microscope. Now it clearly outlines that geo-based titanium doped cobalt oxide samples show the clear cut, the slabs, sheets. If same images of the synthesized graphene doped, this is a graphene doped titanium cobalt oxide. Okay, this is the graphene doped pure cobalt oxide, graphene doped titanium cobalt oxide, 1%, 2%, all this. This is the nanosheet like morphology traced here, detected. Okay, now you see this nanosheet like morphology. After dope means taking the base of the geo. See here the length and thickness of the sheet, 2160 is highest for P, this one. Now you see, it is very interesting. because the material, as I talk about the bulk and nano, how the bulk material changes its properties at nanoscale level. So here the photocatalytic activity. So for this 0 to 180 minute for pure increased. Okay. This absorbance for this increased up to this, then this, and here decreased. Now this is the case. Effect of radical scavenger addition on photodegradation of EMB and EMO mixed dye under sunlight over GTCO1 nanocomposite calculated by UV-VIS. Okay. This is the effect of radical scavenger addition on photodegradation of EMB and EMO. So these are the material and scavengers. Okay. Now this is the case. Now here the graphene oxide based nickel doped MnO2. Now you see this work has been published in Material Science in Semiconductor Processing. Okay, and now you see the effect of this nickel doped. Okay. These are the materials. Hello.
Hello, sir.
Rafi sir. Okay. Am I audible? Okay. Now you see the XRD results, which outline here that all samples have monoclinic crystal structure with delta phase of MnO2. Okay. Now this is the case. These are the XRD patterns of PMO, GMO, GNMO, GNMO3 and GNMO5. And these are the lattice parameters. Now you see the same images, if same images. Here the nanoflex-like morphology was detected. See here, very interesting. These are the nanocomposites. This is the cyclic voltagrams of ice prepare samples. These are the charge discharge curves, galvanostatic charge discharge curves of ice prepare samples, specific capacitance of all ice synthesized nanocomposite samples. And here is the reduced graphene oxide iron doped alpha MnO2, published in the Journal of Energy Storage, and its impact factor is 9. Here is the nanowires, nanocomposite materials, smart materials. Now this is the tetragonal cubic phases of MnO2 was found, and these are here. Tetragonal phase of alpha MnO2. These are the materials. So here is the RGO, reduced graphene oxide, and its lattice parameters you see. A is this one, C is this one, hexagonal structure. Okay. Nanorods and nanowire like morphology was found. So these are the cases here. Indal. कधी नाही कशाची नोट काय नाही काय एक एक 5 मिनिट एक 10 मिनिटं येतो मी काय ते आता ती तिकडे आलेली का मला काही ट्रेस होईना आमची नोट आलेली आहे कशाच्या संदर्भात नाही बर बघू आपण ते मी येतो हो 10 मिनिटांनी येतो मी cyclic voltograms of these materials. We have performed this and we performed this experiment and calculated the this charge discharge of all these what is the current density of the material, the performance of the material we calculated here. And this is the galvanostatic charge discharge curves of all the samples. Okay. Specific capacitance of all ice synthesized samples. Then this is the case here. Time dependent absorption spectra of PMO, GMO, and all these materials. Okay. Now this is the plots of time versus C by C0 and log of C0 by CT. All these. Now here also the work tungsten decorated reduced graphene oxide based iron nickel co-doped MnO2. Here also this work published in 9.4 impact factor. And these are the materials. Here the same images of tungsten. This is the, as I mentioned, that one tungsten decorated GO based 3% iron nickel doped. And this is the graphite electrode. This is the counter. This is the reference electrode. and this is the working electrode which we prepared the material. Okay. Now the material has the cubic and tetragonal phase of this, and for this Mn alpha Mn2O3, and this is the tungsten carbide. Okay. Now the tetragonal and cubic phases of MnO2 found here. XRD patterns of TGO, MnO2, all these samples. This is the nanospheres here clearly outlined. Rods also, nanorod and nanosphere. Okay. See the morphology of the material. And this is the cyclovoltograms. Okay. And galvanostatic charge discharge curves of the synthesized samples. Here is the potential versus time, and here is the current density versus voltage. Now the circuit of this active electrodes in this, and this is the capacitance retention. The electrochemical parameters of as synthesized samples. Here is the specific capacitance and the solution resistance. Bilayer N-doped tungsten modified. Okay. Tungsten N-doped modified samples. This is the intensity versus 2 theta. These are the XRD patterns, and these are the crystallographic lattice parameters of SPP sample. And see here the nanosheet-like morphology. Okay, so this is the nanosheet-like morphology. See here the material, the quantity is very small, and it is in powder form. But the powder form of the material at nano level, see here, clear cut nanosheets. And this is the two-dimensional material. And this is nothing but the cyclovoltograms. Here we have to find out the current density of the material, okay, and efficiency of the material. Then using the galvanostatic charge discharge curves, we can find out the here how much time it takes for the discharge. If it enhances, then better material performance. Here the current, as I stated this. Now what is the future scope of the advanced nanomaterials? Graphene functionalization and its applications. Graphene, a 2D dimensional nanomaterial with exceptional electrical, thermal, and mechanical properties, is a key focus in cutting-edge nanotechnology research. The functionalization of graphene by introducing heteroatoms, surface modifications, or hybrid structures enhances its applicability in various fields, namely biomedical engineering, photo supercapacitors, solar cells, and water purification of these two-dimensional materials. Below is the future scope of graphene functionalization in these domains. Graphene functionalization for biomedical applications, and future scope of this is for the drug delivery, biosensors, and diagnostics. So tissue engineering and regenerative medicine, antibacterial and antiviral coatings, these two-dimensional materials, namely silver and zinc oxide, copper for antimicrobial coatings in hospitals and medical devices. Graphene functionalization for photo supercapacitors, and it plays a very vital role for this. If we use the graphene quantum dot hybrids for enhanced photo charging, combining graphene with perovskite quantum dots or carbon dots can boost light absorption and charge separation. Okay. Now graphene MGen composites for high performance electrodes. Now MGENS and graphene hybrids can improve capacitive energy storage and the cycling stability. Graphene based. So these are the flexible and variable photo supercapacitors. Graphene as a transparent electrode for light absorption enhancement. Functionalized graphene films can replace indium tin oxide for transparent electrodes, making flexible, transparent, and efficient photo supercapacitors. So these are again graphene functionalization for solar cells and graphene perovskite solar cells. So graphene in tandem solar cells, graphene based transparent conducting electrodes, graphene quantum dots, okay, for light harvesting it can be used. These are the graphene functionalization for water purification. So what is the future scope of this one is the nanofiltration membranes. We can again the graphene enhanced photocatalysis for wastewater treatment. So graphene TiO2 or graphene ZNO composites for degradation of organic pollutants using solar driven photocatalysis. Graphene as an adsorbent for heavy metal removal. So it can be used for the heavy metal removal. Graphene based antibacterial coatings for water filters. Thank you. I have covered here the many topics of this one relating my research. If you have any query, a question, you can ask. So thank you for listening my talk very patiently and very sincerely. I owe my sincere thanks to the director, Professor Dhansri Mahajan Madam, and Deputy Director, Professor Rafe, for giving an opportunity to share my ideas and my research work with the participants in MMTTC. Thank you for listening very patiently. Yeah. Oh.
So, on behalf of UGC Malviya Mission Teachers Training Center, Dr. Babasaheb Ambedkar Marathwada University, my special thanks to Professor B.N. Dole sir for sparing his valuable time and setting the tone of this event through his inaugural address as well as a technical session. So, I'm really thankful to you, sir. And with the permission of the resource person, I declare that this technical session is over. Thank you.
Thank you. Thank you.